everyone, these are the solutions for the one-to-one and inverse functions day 2. So notice that the first thing that we have to remember and have clear is that for a function to have an inverse, it must be one-to-one, even if it's one-to-one in a very specific restricted domain. Now, here in the first question we have, is f of x for x minus 2 one-to-one? And so we know that it is. It's a line, and lines are one-to-one. So now we can find his inverse. So the first thing that we do is, so we have y equals 4x minus 2. We're going to switch the input and the output. And now we have x equals 4y minus 2. And now we're going to isolate and solve for y. So now we have that x plus 2 is 4y. And then x plus 2 over 4 is going to be y. And we have that f minus 1 of x is the function x plus 2 divided by 4. Now we can find certain values. Notice that if we do f of 2, here it's asking if we have any relationship between f of 2 and f minus 1 of 6. And f of 2 is clearly 6, and we take f minus 1 of 6, plug in, we have 2. Well, this makes sense because f of x is equals y implies that f minus 1 of y is equals x. So they have this inverse relationship. The 2 is going to 6, and so the 6 goes back to 2. So that's why it's called an inverse. Question number 2 says, okay, so let's g of x be x over x plus 4. And clearly this is defined on minus infinity minus 4 to minus 4 infinity, since this cannot be 0 in the denominator, so it cannot be minus 4 in the denominator. We want to find the inverse here. And so we do what we always do. First, we switch x by y, and then we're trying to solve and isolate for y. But here's a little bit tricky. So what we have to do first is to be able to isolate y, we need to multiply to the other side. So x is going to be multiplied now by y plus 4, and we're going to have to solve from there. So notice that now we have y plus 4 times x is equals y. And so to be able to get all the y's in a single side, I need to multiply this out, and I get y times x plus 4x is equals y. So I need to now move yx to the other side, so we have common terms in y. And then now I need to factor. So y is a common factor in here, and so y is common factor of 1 minus x. And then by isolating y, I'm going to find out that y is 4x over 1 minus x. So notice that this is a little bit more difficult than the common process that we do for normal finding the inverse. This requires a little bit more of algebra and a little bit more of equation solving. But we are essentially doing the same process. The process behind is just switching input with output and then isolating y to be able to find the inverse. In general here, our function g minus 1 then is going to be defined by 4x over 1 minus x. Now, question number 3 gives me a table. It gives me values of x and f of x, and then we want to find out f minus 1 of 2. Notice that because we have f minus 1 of 2, what we want to do is we want to go and take values from the output to be able to go back into the input. So to find f minus 1 of 2, I gotta locate what is the values where f of x is 2. So notice that 2 is here an image of 0. So when x is equal to 0, f of x is 2. So that means that, well, if f of 0 is 2, then f minus 1 of 2 is 0. And that kind of gives me the value. Remember, in the same fashion that f of 2 is 5, then f to the minus 1 of 5 is 2. So remember, we're back and forth. So if they're asking you what if f minus 1 of 2, look for what are those points that are actually gonna provide me 2 on the output of f. Number 4 gives me a graph, and then we're gonna try and find certain values. Notice we're being asked by f of 2, f of a, f minus 1 of 2, f minus 1 of 5, f minus 1 of 6, and then some compositions. Now for f of 2, we can see clearly that it's 5 because we take here the value of 2 on x, and then we look up on y, and so we can see that in there. So we're taking this value and we can see it here, right? F of 2 is 5. Now f of 8, you can see that it's producing a 0, so f of a is 0, right? Now f minus 1 of 2 is asking me, hey, if I go back from the output from 2 on y, what am I gonna get? And so I'm returning here from 2 on the output, and I go through the function, and I'm gonna find out, hey, is 6. Okay? So when I'm calculating, normally when I calculate a function, I goes from x to y. But now graphically, if I'm going from the inverse, I'm going from the y-axis back to the x-axis. In the same fashion, if I'm calculating f minus 1 of 5, then I precisely take this value here of 5, and then that's going to lead me to this point over here, which is going to lead me to 2. Okay? All right, let me remove a little bit of the clutter here so everything can be more clear. But yeah, notice that if I take 5 and y and I go back to the function, it goes back to 2. So f minus 1 of 5 is 2. F minus 1 of 6, notice that this point here is in 6. So it's actually going to be 0. F minus 1 of 6 would be 0 because the function is here, and when it's 6, and we're returning back to 0 through the function. Now we have f minus 1 of f of 5. Well, remember that the composition gives me the identity. So f minus 1 of f of 5 is just going to be 5. It's just going to be the original value. Same thing here, f minus 1 composed f of 6 is just going to give me 6. Since composition of f with f minus 1, it just gives me the value of x. Now for question number 5, we have this graph over here, and this is the graph of y equals f. So this is a one-to-one function, even if it's a broken set of lines. So we can kind of define an inverse here, except for certain points, maybe this ones. So for example, f of minus 2, we can clearly see that is 0 from here. We can find values like f of minus 3, sorry, f minus 1 of 3. If I go to 3, I'm in this point, so I'm going to be here. So that means that it's going to be 6. Picking up 3, checking where the function is, it gives me that is 6. F minus 1 of 5, notice that I'll be taking 5 here on the y and returning, but when I go to this point, then I don't have anything here, so this is undefined. I cannot talk about any point in here. However, if I get to talk about a point like, for example, f minus 1 of 2, then I'm actually going to use this point, and that will be 2. If I go with f minus 1 of 1, notice that 1 in y is the image of 0, so f minus 1 of 1 is going to be 0. And then again, if I make some points here, f minus 1 of f of a, notice that that has no definition here because 8 is not part of the values. Notice 8 here is not defined on the domain. So this is undefined, f of a is undefined, and so because f of a is undefined, then f minus 1 is going to be undefined as well. It doesn't matter that we're doing f minus 1 of f. If the point doesn't exist on the domain, then it's undefined. F of a doesn't exist here, so I cannot do anything with it. Okay? Now, f minus 1 of f of 6. F of 6 actually exists. Notice here, f of 6 is this point, which is 3. So this is like, well, f minus 1 of 3. And I could trace it back. Well, f minus 1 of 3 is really 6. So I get back to the original point from where I'm coming from. And that makes sense because f minus 1 composed with f, it just gives me the value from where we're coming from. Now, question 6 says, consider the function f of x equals x squared minus 1. Plot the graph. Well, we already know that this is a parabola, x squared, that is shifted down by 1. It says, can we define the inverse of x where the domain is minus infinity to infinity? What is the problem that arises? And the answer is, again, no, because we don't have a one-to-one function in the minus infinity to infinity. Now, if we restrict to 0 to infinity, can we find an inverse? And in this case, we actually can't. We do the same that we always do. We set up y equals x squared minus 1, switch x by y. X is equals y squared minus 1. Now we're going to isolate for y. And so that means that y squared is x plus 1. We take the square root. Y is equals x squared root of x plus 1. And notice that because we are in only the positives, then I don't need to write plus or minus. I just leave the plus and that's enough. So that's going to lead me to f minus 1 of x being just a square root of x plus 1. And that's one of the solutions when we don't have one-to-one functions. If we can just restrict the domain to where the function is one-to-one, then we can actually get inverse in those small domains. Now, question 7 is just a quick verification if some of the functions are going to be one-to-one in specific domains. So, for example, x minus 1 squared when x is bigger than 0 is actually not, because this is still going to have pieces that are twice. So it's not only moving and restricting the domain. Restricting the domain is not enough. It gotta be so that with the restricted domain, you have a one-to-one function. Now, another example of that is x squared plus 1 when x is bigger than minus 2. This is not a one-to-one. Notice that this is just like the x squared going up once. And then we're going from x bigger than minus 2. So that means that between minus 2 and 0, it still is going to have similar values with 0 to 2. So that function b is not going to work out. But absolute value of x plus 1 when x is bigger than minus 1 actually is going to work out, because notice this domain is actually splitting the absolute value on the point where this becomes 0. So absolute value of x plus 1 is this function here, and it splits in minus 1, the two different directions of the function. So if I go only from minus 1 to infinity, this part is going to get lost, and this function now is going to be a one-to-one function. So of course, because then in minus 1 to infinity is a one-to-one function, then we're probably going to be able to actually find also an inverse in there. Now with x minus 1, absolute value of x minus 1 when x is bigger than minus 1, it doesn't happen the same. You got to be careful with this. Notice that this point is actually, this absolute value splits at 1, not at minus 1. So if you want to restrict this one, so it's 1 to 1, it doesn't have to be x bigger than minus 1, it got to be x bigger than 1. So you only take half of the absolute value, half of the things, and you don't repeat distance. Okay? So be careful with these restrictions of domain. Pictures are very important, so you can see if you're repeating values or not. So every time that you're checking if in a specific domains a function is one-to-one or not, make sure to check the specific domains and the picture of the function on those specific domains. Okay? And so those are the solutions of the day 2 for inverses.